I am HfO2. Today I am here to present my proposed project, hafnium oxide-based memristors as potential candidate towards radiation-tolerant and thermally stable electronics for deep space environments. So there are several challenges in space, like cosmic rays are there are solar flares, which causes single event effects like bit flips, latch-ups, burnouts, and gate ruptures. The total ionizing dose degrades the material over time, and there are also huge temperature fluctuations. So we have figured out some solutions for these problems, like we use redundancy modules like triple modular redundancy and modular redundancy. We use shielding, but this also comes with some other problems, like it increases the payload, the cost is also increased. There are power constraints, there are miniaturization constraint, and also the data processing speed is very slow, which is unfit for neuromorphic computing. So we have suggested a possible solution which is resistive switching based inorganic or hybrid material memristors. So the Thinfilm and Nanoscience Lab of our department is doing extensive research work in the field of resistive switching. So these are some of the recent papers and these are some of our patents. So since we are working in this field, so we can we have the motivation and tenacity to justify what we are proposing. So first we need to understand what is resistive switching. So what we do, we sandwich a dielectric material in between two electrodes, and then we apply some electric field. So with increasing electric field, we see the current is increasing, but not very much. But after a certain point, we will see that the current increases rapidly, and when we reduce the field again, it will follow a linear path. So this sudden switching phenomena can be used in many memory devices. On the basis of this curve, we can make bipolar switching devices, we can make right-walls read many type switching devices, and we can also make multi-level switching devices. So let us understand the working principle of the device. So when potential difference is applied in between the two electrodes, then a conductive channel of oxygen vacancies is created. And when the vacancies connect, a conductive path for electron is formed, and we call is at a lower resistive state or set state. We represent it as logic state 1. And when we apply the reverse polarity, this channel is broken and we represent it as higher resistive state or logic 0. The hysteresis graph is shown here. So this is the diagram of a typical hafnium oxide-based memristor, and these are some electron microscopic images. So this table shows the advantages of hafnium oxide-based chips over silicon chips. So we have also studied, we have gone through the literature. We have also studied the radiation behavior of hafnium oxide. Hafnium oxide shows very good radiation tolerance. We can see in the first graph that radiation didn't affect the working of the device very much. In the second graph, we can also see the LRS is almost unaffected, but HRS is a bit affected, but this is not an issue because LRS is fixed. It will not damage our device, or it will not create any problem in the working logics of the system. So there are other additional advantages of using memristors in our systems, like memristors are high density memory. That means we can reduce the cell size. Crossbar arrays of memristors are possible. We can also stack multi-layers, one on the top of other, and we can obtain multi-level switching with the help of memristors. Like in typical memory, we can save one binary number, like we can either save 0 or 1, but in case of memristors, we can save up to 4 binary numbers, like we can define it that 4 states will define have 4 designated numbers. Like lateral arrangement of the device can also be implemented as a sensor. So it can be work as a sensor itself. It will be the memory location for the sense data. Then hafnium oxide is not only hafnium oxide but any type of memristor shows neuromorphic behavior, which is very important in case of AI applications. Using memristors, we can use in-memory processing. That means we don't need any processor. The memory can itself do the processing task. The material hafnium oxide is itself CMOS compatible. That means we can implement this material directly into the gates of the CMOS and it will work fine. So all these things shows that hafnium oxide is a very versatile material for electronics. So there are several research gaps in the scope of study. Like all the things that we have discussed are tested in ground-based facilities, but we don't know how the thing will actually work in space environment, how the temperature cycles will actually affect this, or how the total ionizing dose will affect this. So we need a platform to test this, test the performance of these chips. So for that we are seeking, we can install or incorporate these chips into the PSLV stage 4, so that the characteristic studies of these chips can be studied rigorously in actual space environment. So these are the 3 advances. Thank you.
So one question is, what about the limitations of the operating frequencies, switching frequencies of these kinds of devices?
So mainly the data that is available in case of memristors, these devices are mainly implemented in, we work in DC. Means you are telling that the operating frequency.
How fast you will switch?
Sir, it is like
Compare. What is the each generation? Each generation. How will you compare?
It generates less heat because we are not using any charge storage containers. Like in traditional RAMs, we use capacitor for charge storage, but in this case there is no charging or discharging of capacitor, so there will be no additional heat generated.
Okay, and since this phenomenon of hysteresis drives the whole story, this hysteresis is dependent on the external factor, like say the temperature.
Sir, we can make memristors with the help of many materials. We can work on that. Like if we want it not to change with temperature, then we can make it like it will be temperature resistant. If we want to make it like use it like a sensor, then we will choose such materials so that it can be implemented as a sensor.
How reliable are these systems? Precision.
So these systems are quite reliable. This is the emerging field of study. Basically, China, Japan, these countries are mainly working on this. So we are concerned, all are concerned about AI. So the main concern is we can't. The future is AI, but we can't think about AI without the help of neuromorphic computing. So for neuromorphic computing, we need these devices. Today or tomorrow, these devices are actually coming into the market. So big companies are working on this.
So the space system is saying PSLV space system.
Sir, I am suggesting to check.
But in this can also be faster, so in the space in our way that productivity skills are switched on, switched off.
Yes, sir, that can be also done because all the things that we have studied on Earth, means nobody has taken any memristor to space yet.
You want already published, right? You say that it is already published.
No, sir. These are basically some research papers from our Thinfilm and Nanoscience Lab that are mainly organic based. This is a material as proposed is an inorganic.
Okay.